Now we are set up to operate and start the laser. The beam will go from the laser head to the setup autocorrelator, which will show us the pulse duration.
That means we can directly see the sub 50 femtosecond pulse duration now, or what result do we expect from the device?
Not so easy. The device itself shows the autocorrelation, which is a convolution of the pulse with itself. So it's an indirect measurement of the pulse duration, showing a slightly longer pulse. All right, now we are ready to start the laser, and all we have to do is take the controller box and push the on button.
Yeah, we can see here in the background the screen of the controller box in a larger view. You have the simple on and off button for the laser. You can see in the right corner some measured some output power and the actual status. There's some blinking light which indicates that the laser starts. And now we can see the laser is running at full power, and you can directly see the autocorrelation.
All right, now we would like to show you the feature of dispersion precompensation. For this, we have prepared 6 Brewster plates of BK7 material. Each is 6.35 millimeters thick. And if we put these 6 plates into the beam, the pulse duration will increase.
Yeah, we see here in the background the measured autocorrelation, which is a live measurement. And the 54 femtosecond autocorrelation belongs to a 40 femtosecond pulse. And if we put some material in the beam propagates over here.
All right, now we put the plates into the beam, and you can check what happens to the autocorrelation.
So what you can directly see, the pulse gets much longer, and also the pulse signal is smaller, which means we lose a lot of peak power due to some additional material. This could be the demo plates, this could be an optical setup like a microscope, some lenses, or whatever is planned after our lasers. And yeah, now we have the possibility to tune the internal chirp of the output to have a short pulse at the target on the biological sample or whatever is the target. And yeah, can you show us
yes, exactly.
how it works?
It's very easy to do this. You just go to the controller box and press these buttons, the plus and the minus buttons, depending on your material. And if you press one direction, in this the negative chirp, you can see that the pulses get shorter and shorter, and you can go even further, and then the pulse gets longer. So we exceeded the maximum. Now we go a little bit back. And we have the same pulse duration again. So this way, you can easily, on the fly, optimize the pulse duration on your sample.
Which means now we have a slightly negative chirp output and some positive dispersion from the material to get a short pulse on the sample. Now we want to show you some second harmonic generation. I switch on the laser. Now the laser starts. We have prepared something. We have here the output beam of the laser going here to an acrylic mirror, where the frequency doubled light is directed towards the power meter. We can see here the actual power, and the remaining infrared light passing here and going to a beam dump. The laser is running, and with the pulse laser and the short pulses, the frequency doubling is really easy. All what you have to do is you need a lens to focusing in the crystal to reach the high intensity, and then we have the high peak power due to the short pulses, and we need a crystal. We have prepared here a lens. It's like 35 millimeter focal length. Put it into the beam, and then we have here 1 millimeter BBO crystal. If you put it in, we get directly the first green. Now we have to optimize the phase matching a little bit. That's that. And now we get 100 milliwatts of green from the laser. And yeah, we measure here the green. Now the pulse duration is at about 40 femtosecond. We have here in the backside, we can see the controller menu. And in the middle, there is the actual pulse duration, which is factory calibrated to make some autocorrelation measurement over motor position and make some calibration. And now we can change it, and I can show you what happens if we go to much longer pulses. So we go down to like 200 femtosecond pulse duration. We see we have only remaining 12 milliwatts of green. But we have the same average power on the crystal or on the target, which is a disadvantage if you need a certain power on the target and you want to have the lowest power as possible, that the cells lives for a while and don't get destroyed. But you want the high nonlinear signal. Therefore, the short pulses are that important for such applications. If I go back with the pulse duration, you get much stronger signal, or later in your microscope, a much better contrast due to the high peak power. So now we're a little bit too far. We have to go back, and you can easily optimize it by clicking on the controller or via your smartphone or your computer to optimize it to your microscope signal. So what we have seen is that the laser works turnkey. What we don't have seen is the laser is really robust. And we know this high peak power lasers are really, really sensitive normally. And yeah, we thought about how to check if the laser really works well in all conditions. And what we have shown is that we can make some frequency doubling, and the frequency doubling depends on the average power, depends on the peak power, depends on the pulse duration. It's really sensitive. And we have prepared here the setup, and we want to show you how robust the laser is. Can you switch it on?
Yes, I just switch it on here, and it will take a few seconds. And in the bottom left part of the screen, you will see the power that is generated in the second harmonic crystal. So after a few moments, the laser will start, and you will see an increase in power to about 100 milliwatts. Jan, what can we how can we demonstrate the stability of the laser?
I have a hammer. We can knock on the table, but it's hard to see if really something happened.
Yeah.
Do we have something to visualize the vibration?
Yeah. Let me see if I can. Let's take a €2 piece, put it on top of the laser. Let's see if you can flip it.
Not really. Shakes a little bit, but I think we need a bigger hammer.
All right. What do you think about this one, Jan?
Oh, this sounds good. Let's check it out if we can.
All right.
Yeah, really hard shock, but laser's still working.
All right.
I think it's really robust.
Yeah, I think we've shown you and proved that the laser system is really stable. And if you have any doubts, this will show you how stable it is.
Great.
Great.